Recording in progress.
So, good morning, everybody. It is my pleasure to start this new series of 7 by introducing Peter Jossen. So, Peter, well, after studying Bitcoin in the in Lausanne, he got his PhD in Hungary, in Central European University. And after the series of postdoctoral acquisition in Germany, Regensburg, then Paris, and in ETH in Zurich, he joined King's College in 2022. 22, right?
Something like
Something.
Yeah.
Well, and today he will give a talk on functions, exponential integrals, and their differential equations.
Hi, thank you very much for the introduction. Thank you very much for the invitation as well. It's a pleasure to be here. May is anyway, in my opinion, the best month to visit Lisbon after it gets too hot. Good. So I'm talking about E functions and exponential integrals. And let me start with a little bit of history, some very classical topic in mathematical physics, which is the theory of Bessel functions. So here I'm considering the Bessel function in the complex variable z with an integer non-negative parameter k. And one way of defining it is simply writing a power series. It goes like this, n from 0 to infinity, -1 to the n, z halved to the power 2m plus k, and you divide this by n factorial, n plus k factorial. As such, well, it is an entire function. It has an infinite radius of convergence, and it tells you not a lot about the Bessel function. This is almost like someone in first-year calculus introducing the sine function or the cosine function just by writing a power series and say, well, here it is. It satisfies a differential equation, namely, well, the so-called Bessel differential equation. It reads like this: z square second derivative plus z first derivative plus z square minus k square u is equal to 0. I hope I got this right. Yes. No sign errors. So this is the Bessel differential equation. This power series is one solution of this equation. Well, there will be another linearly independent one, which is not a holomorphic function, but which has some monodromy around 0. This here is the Bessel function of the first kind. The other solution is the Bessel function of the second kind. Good. So why are these functions interesting? They have real zeros, and if I plot the Bessel functions here of the real variable z, they look a little bit like this. So J0, it starts and oscillates like that. This is J0. J1, well, if k is 1, you see it has a root at 0. It goes a bit like this. The zeros interlace. So that would be J1, and then J2, well, it has a double 0 at 0, and again, it oscillates like this. Voila. And the mathematical interest of these functions is that the roots describe eigenfrequencies of a vibrating membrane. And so this explains, switch blackboard now, this mystery picture here. So imagine you have a circular drum and you hit it somewhere. Well, then the vibration of the whole drum is a linear combination of well, eigen frequencies the base frequencies where just the whole membrane goes up and down, but then there is a vibration mode where you have one line that is fixed, and when this side comes out, the other one goes in. There is also a vibration mode with a concentric circle, which remains fixed, and then there's other combinations with various fixed diameters and fixed concentric circles. And so if this frequency here is normalized so that it is the first zero of the zeroth Bessel function, let's say little j01, then this here is a frequency that is the second root of the Bessel function j0. This here would be a frequency that is the first root of the Bessel function j1. So that would be this number here, and so on. So this is the relation between roots of Bessel functions and eigenfrequencies of a circular membrane. Now, in like late 19th century, there was a famous problem around called Bourget's hypothesis. Which at the time was advertised as something that we will not solve in a million years. A problem that was considered untractable. And it is like this. If you have a common root of two Bessel functions, then, well, that was the question, either z is equal to 0, or, well, the two Bessel functions are actually the same Bessel function. So different Bessel functions cannot have common roots except the root 0, which is trivially there. So there's a physical motivation for this, because if any two different Bessel functions had a common 0, then, well, there would be two eigenfrequencies that pile up, add up together, and you would hear. So there would be an amplification of that frequency in the vibration of the membrane, and that could have, I don't know, there could be some catastrophe, blackout or whatnot that could happen because of that. But, well, numerical calculations suggested this does not happen. So one of the persons to be interested in this Bourget's hypothesis is Carl Ludwig Siegel. And in order to study the problem in the, well, in fact, exactly in 1929, introduces the concept of E functions. So let me give you the definition of E functions. So an E function with rational coefficients is a power series. Well, and from 0 to infinity, coefficient an over n factorial z to the power n. I'll call it f of z. So the an's, of course, are rational numbers like this. And there's two conditions to be satisfied. One is that the absolute value of an and also the common denominator of, let's say, A0 up to AN, both of these quantities are bounded by a power of a constant. So this one is less than some constant to the n. This one is less than some constant to the n for all n greater than 1. And but the quantifier is here. There exists a positive constant with this property. So in absolute value, these coefficients, they grow at most geometrically, but also there's an arithmetic part in it, so that there's a common denominator for the first n coefficients, which also doesn't grow faster than a geometric sequence. The second condition is, let me write it like this, L of f is 0 for some non-zero L, which is a differential operator. Like this. In other words, the function f has to satisfy a linear differential equation with polynomial coefficients.
What does it mean?
Then is least common denominator of A0 up to AN. So these are rational numbers. If you multiply all of them by a sufficiently big integer, you get integer numbers. But and the smallest such is like the common denominator. So this is E functions with rational coefficients. In general, an E function is a algebraic linear combination of such. So Q-bar linear combination of such. There's of course another way of defining E functions, not going over rational coefficients first and then doing this, but we can also directly express, like instead of the absolute value, you would need to talk about the absolute value of Galois conjugates and so on. So there's another possibility. So these are E functions. Closely related is a variant of the concept, which is the so-called G functions. And it's exactly the same definition, except that you lose the factorial. So a G function is exactly the same, but you don't put the factorial. So here, one thing you can see, because of this condition here, E functions, they have an infinite radius of convergence, so they define entire functions. G functions, they have a finite positive radius of convergence. Good, so some examples of these are, well, let's start with a silly thing, so polynomials. Then, of course, the exponential series, to put all the coefficients an equal to 1. But then, well, also all the Bessel functions. It's not hard to verify. And there's other power series that you can write down explicitly, so-called hypergeometric series, if you choose the coefficients right. Once you have a stock of E functions, you can do things to them. So sums, products, derivatives, primitives with properly normalized integration constant, as long as it's rational or algebraic. So sums, products, derivatives, primitives of E functions are again E functions. So there's a lot you can do. So exponential polynomials, for example, sine, cosine, and so on, they're all E functions. You can do Hadamard products. So there's like the freshman's product where you multiply 2 power series just by multiplying the coefficients. That's also something you can do with E functions. So there's a wealth of these around. Many functions in classical physics are E functions. You just open some book on special functions, and you will certainly find all chapters written on certain E functions. The Airy function is another nice example. So how does this help now? There's the central or most important theorem now around E functions is the so-called Siegel-Szydlowski theorem. And I would add as authors also now Yves André and Fritz Beukers. And it states this. So first, informally, you take an E function, which is not a polynomial, and you evaluate it at any non-zero algebraic number. And then, well, except if it's wrong for trivial reasons, the value is transcendental. So values of E functions are transcendental whenever you expect nothing else. Let me write it properly. So let f1, fn be E functions. Solutions of a common differential equation. So each of the E functions satisfies a differential equation. You can always cook up one that annihilates all of them. Take alpha, an algebraic number, which is not 0, and which is not a singularity of the differential equation. Then, well, every relation between the values I should be precise, so more precise. So every algebraic, every polynomial relation between f1 of alpha, fn of alpha lifts to a polynomial relation between the functions. Yeah, so you have, there exists a polynomial relation between the functions, so that when you specialize z to alpha, you get your given relation between the values. So this is the version of Fritz Beukers that is explained in a nice article called A Refinement of the Siegel-Szydlowski Theorem, something like this. You can find this on the archive. That version here is
coefficients of the polynomial. The coefficients of the polynomials.
So here the coefficients of the polynomials are algebraic numbers, and here, well, there are polynomials in Z with algebraic coefficients.
Thank you.
So one case is you take a transcendental E function and some non-zero alpha, which is not the singularity of the differential equation, then the value at alpha of this transcendental E function is a transcendental number. Now, Fourier's hypothesis is a corollary of this. How so? Well, if you have a common zero of two Bessel functions, which are different, then it is not terribly difficult to show. Then this common root, Z0, is a root of a polynomial with integer coefficients. So then this Z0 is in particular algebraic. And that follows simply from differential relations between these Bessel functions, and that the differential order of the equation is 2. So this was known. Well, but then 0 clearly is an algebraic number. And the Bessel function satisfies a differential equation which is non-singular outside 0. So JL of something is algebraic, the something cannot be algebraic, turning this thing around. So the only possibility is Z0 is 0. So this transcendence theorem solves the mathematical physics problem of common roots of Bessel functions. So JK is a transcendental E function. So if JK, you plug in an algebraic number alpha, this will be transcendental unless alpha is 0. But Z0 is a root. So JK of Z0 is, well, 0. 0 is an algebraic number. So Z0 cannot be an algebraic number.
Understand, but why did we know that it was algebraic in the first place?
This has to do with the differential equation and the differential relations between JK and JL. It's a small calculation. So you take J0, you derive it, and you will see that it's a linear combination of J1 and J2. And then you derive it a second time, you find this linear relation. So ultimately, you will see that.
But you said it after consequence of this theorem.
No, there's two separate things. So first, this here it was no, it is easy using the differential equation of the Bessel functions. This was known before. So if two different Bessel functions had a common zero, that common zero would be an algebraic number. And then this is the hard part. So this conclusion here is using the Siegel-Szydlowski theorem turned around. So the values at algebraic numbers are transcendental. So the roots in particular cannot be algebraic numbers. So they're transcendental. There's another good example. Now I should move on, but there's another really good example of an E function, which is e to the z minus 1. It's an E function, and it satisfies a differential equation with constant coefficients. So there's no singularities in the differential equation. So what we conclude, if for any algebraic number alpha, e to the alpha minus 1 is transcendental. Now, if you plug in for alpha 2 pi I, you find 0. 0 is not transcendental. So that means that 2 pi I cannot be an algebraic number. Therefore, pi is transcendental. You can push this, the Lindemann-Weierstrass theorem on algebraic independence of exponentials is a corollary of the Siegel-Szydlowski theorem. Probably part of the motivation of Siegel, but he doesn't write really what his motivations are. So we're left to guess. Good. So now I'm going to talk about something completely different. This is history, ancient to early 2000s now, in collaboration with my colleague Javier Fresán. We are interested in a class of numbers that are called exponential periods. So let me write down the general shape of such a number. So these exponential periods, they are defined by definite integrals. Say we integrate, I will explain later. We will integrate over some domain sigma, and the shape of the integral is exponential minus some function f. The minus is there just by tradition, times some differential form omega. And now I have to tell you where the omega and the sigma and the f lives. So to write this down, we start with an algebraic variety x. It has to be defined over a number field, so defined over q bar. Then in this algebraic variety, we are always going to pick some closed subvariety. Now, the f is a function on x, a regular function. So we see it, one way to see it. It's just a morphism to the affine line. So this is, if you want, f is a regular function on x, like this. Then, well, omega is a differential, let's say, n form on x, which is closed in the sense that the differential of e to the minus f omega is 0. And finally, sigma is a, let's say, topological cycle on the complex points of x with boundary in y. I'll write down a couple of examples in a minute. One of the flexibilities here that we allow is that the sigma, this topological cycle, does not need to be a compact cycle. So it can go to infinity somewhere, but it must go to, if it goes to infinity somewhere, it must go to infinity in a direction where the real part of f goes to infinity. That makes the integral converge. So the keyword here, if you want to look up, this is called rapid decay cycles. And rapid decay refers to, well, the exponential decay of the integrand here. So letting x, y, f run over all the algebraic varieties and subvarieties, letting omega and sigma run over all the differential forms and topological cycles, you will get a class of numbers like this. They form a ring. So these are complex numbers. They form a countable subring of the complex numbers. This subring contains the algebraic numbers, and well, since it's countable, there's plenty of complex numbers which are not exponential periods. The game here is to understand transcendence or rationality or algebraicity of these numbers, but even more so if you have several of them, understanding the algebraic relations between them, if there are any. And of course, if they come from somewhat geometrically related varieties, you can expect some relations between them. And in general, you don't expect any relations between exponential periods. So let me give you examples. Number one, this was one of our motivating examples, is the integral from 0 to infinity. See, I really start already with a non-compact cycle, so it goes off to infinity, exponential minus x to the power b, let's say x to the power a, dx. So a and b, they are integers, at least one. Fine, this is a nice converging integral. There is well, where do we integrate? So here the variety is just the affine line. There is a boundary of the cycle at 0. So I'm going to mark 0 as a distinguished point. Then the cycle goes off to infinity. That's fine. This is exactly this rapid decay behavior here. And well, the function f, since x is the affine line, say with coordinate x, well, a regular function is just a polynomial in x. The polynomial is x to the power b. The differential form is x to the a dx, and sigma is, well, this. All right, so that explains the ingredients here. And what do we get? This is 1 over b gamma of a over b. Gamma is the gamma function. It's not hard to see. You just change the variable t is x to the b and use the definition of the gamma function. So special values of the gamma function, by special values, I mean at rational arguments, special values of the gamma function are particular examples of exponential periods. And there is a conjecture about polynomial relations between special values of the gamma function that is pretty old. It's due to Lang and Rohrlich. It's a precise conjecture. What are all algebraic relations between special values of the gamma function, say with a fixed denominator b? And well, there's a transcendence conjecture about exponential periods, which implies conjecture, which specializes to this Rohrlich-Lang conjecture. What else can I do? Well, usually these exponential periods, they don't have names. So you can write down other integrals. Playing over the affine line is very interesting. We can choose, for example, here another polynomial, say monic of degree b, and just write down the same integral. But we get some numbers, and well, they are what they are. They have no specific names. Here's maybe one that's vaguely interesting because, again, the constant has a name. So e to the minus xy dx dy converges nicely. Here, the variety x is the affine plane. So there's a two-dimensional example. I have a two form here. So this is omega. This is y. And then the cycle sigma is all of this. And that's my domain of integration in the affine plane. So this is the real affine plane. And this number here, sometimes written capital G, is the so-called Gompertz constant. I was told it has some meaning in mathematical biology, or it's an interesting number. It's not known whether it's rational or irrational, or even transcendental. So there's, well, guess is that it's a transcendental number, and the period conjecture, the transcendence conjecture for exponential periods would imply that it is indeed a transcendental number, algebraically independent from pi and e, like everything you expect, but we don't know. Good, let me give you one more example, which is related to this Gompertz constant. So let me augment the y a little bit and add the two more lines. So now the y, the subvariety in the affine plane, is here. So y is 0, y is 1, x is 0, which is 1. So 4 lines in the affine plane. And now I have just made a nice square in the affine plane over which I can integrate now. So let's take this sigma here, this little square, and integrate over here. So the integral now becomes, of course, this. So 0 to 1, 0 to 1. And well, this integral, again, it is what it is, but you can write, since we are doing here now an integral over a compact cycle, I can just expand the exponential function as a power series and compute the integral term by term. So before that was not possible because I integrate over something non-compact, and integration and sum don't commute. Makes no sense, but here actually that works. And what I find is this is a series. So -1 to the power n plus 1. This is what I get when I integrate with respect to x, and another n plus 1. This is for the integral with respect to y, and then there's the n factorial of the exponential series. That's the answer. Well, now the question is still, is this a transcendental number or not? And now, if you stare at it a little bit, you will see that this is indeed the special value at, say, z equals 1 of an e function. So let me put in that decoration. I will put here z to the power n. And if I want this to come here, that's where I put the z. All right. So not hard to show. This is an e function. You have to understand the least common denominator of the numbers 1, 2, 3, 4, up to n plus 1. Well, that is bounded by a constant to the power n by the prime number theorem. So there's the prime number theorem that goes in. It satisfies the differential equation of order 3, not hard to show. And then the absolute value of the constant of the coefficient is well, always less than 1. So no problem with that. So it's an e function. It's a transcendental e function. It satisfies the differential equation. The differential equation is non-singular outside 0. So Siegel-Szydlowski says this is transcendental. So call this maybe, I want to call it a P of Z for P for period. So now I have, instead of a period number, I have a period function. And here P of 1 is transcendental. That's by Siegel-Szydlowski. So sometimes Siegel-Szydlowski can give us instances of transcendence of exponential periods. But then if I'm going back here, special values of the gamma function, they are not expected to be special values of e functions. But first, the gamma function itself is not an e function. That doesn't satisfy a differential equation, really, so no chance. And there is philosophical reasons why special values of the gamma function, they should have nothing to do. They should be algebraically independent from all values of e functions. So we don't know that, but we don't expect that the Siegel-Szydlowski theorem solves for us the problem of transcendence of periods. So the question is now, well, why does it work sometimes and sometimes not? And what's the general picture? So sometimes we find numbers that are not, well, have nothing to do with values of e functions, and sometimes we find exactly values of e functions. So I give you a theorem that is by Javier Fresán and myself. And it's a structure theorem for functions of this kind. So for exponential period functions, or say for exponential integrals that depend on a parameter z in this way. let's say, I write 2025, so it looks like we are still working. But we didn't do anything this year, really, but we plan to. So this is theorem. Again, so let X over Q bar be algebraic variety. Sorry, Y inside X closed. F from X to Jaffenline a regular function. Then we can, again, as I'm not telling again what the sigma and the omega is, so we can form this integral e to the minus f omega, and now I'm putting in front of the f, I'm putting a parameter, and I call this p of z. So this converges for, so I say z close to 1. Okay, so this function can be written as a finite sum of terms. So here, constant times z to the a times log z to the b times e of z. And in this expression, let me start from the right. So e is an e function. B is an integer greater or equal 0. The exponent here can be a rational number, because it can be a fractional exponent here. And then the constant c in front is a complex number, but we can be more precise. So it is an element of the ring generated by algebraic numbers, classical periods. I'll say in a second what this is. Special values of the gamma function, and the last little guy I need is the Euler-Mascheroni constant little gamma. So classical periods, I forgot to say this before, are just like exponential periods when you put the function f to be 0. So if you take out the function f from the story, you get, again, a class of complex numbers, and they are the classical periods. And they are investigated already for a long time. And there's transcendence conjectures for them, starting with Grothendieck, Yves André, and Kontsevich, Sagier. So this is a very well-documented story. When you put the function f to 0, so there's no exponential part in. So classical periods, they include numbers as pi, logarithms, special values of polylogarithms, zeta values, and so on. So it's an interesting class of numbers. The coefficients here, so that's why I'm talking about it, the coefficients. If you want to write a p as a linear combination of e functions and some monodromy factors, the coefficients are not arbitrary complex numbers, but classical periods, some gamma values that we have seen already appear, and also the Euler-Mascheroni constant you need. So one way of seeing the Euler-Mascheroni constant is the derivative of gamma at 1. So actually, it's special values of the gamma function and its derivatives. Bless you. Good. So does it help? Does it help with transcendence? Not really. The problem is now here we have, but if you specialize z to 1, we have the special values of the e functions, but we also have these classical periods, and we know nothing about the relationship, the interaction between classical periods and special values of e functions. Conjecturally, the two rings, so both special values of E functions and classical periods. They're both rings inside the complex number. Conjecturally, the intersection is just the algebraic numbers. An illustration of this is, I know, a very popular problem of and the answer is, well, Siegel apparently didn't know how to produce any other ones, but here is a source of E functions, and it's simple. Just take your favorite algebraic variety, take your favorite function, and you will find these period functions. And it's not difficult. It's actually not so difficult to extract the E functions from this expression. Right? So it's the holomorphic parts here, so you can extract those with a little bit of patience. So this gives you a source of E functions.
You see, for example, people working in number symmetry have plenty of examples of this context, like lambda Winsor model.
Okay. Good.
Could you please give us some?
I give you some. Maybe I think it's an excellent, good suggestion. So examples. So here is one. Take for f. So I start with this. X is GM. So it's the affine line with the origin removed. A regular function on this is nothing else than a Laurent polynomial. So f is let's say x to the minus q plus plus x to the p. So p and q are integers. I want it not to be a polynomial on one or the others. Good. So the y, I'm just taking it like t. So what can we do? Well, here is my punctured affine line. So this is the complex picture. And of course, I can just integrate around 0. So this is a cycle with no boundary. That's fine. And I have differential forms, let's say dx over x or something classical like this. And then the period function is like this, e to the minus z times f of x dx over x. So that is call this p of z. Is it an E function? Well, for sure, since the cycle is compact, you can use Cauchy residue formula. and you can write down this as a power series. So it's an entire function. It's no monodromy in it either, but it's not an E function. So very close. So this is 2 pi I times an E function. And 2 pi I, of course, a classical period. And it is, well, here you can even say the 2 pi I is a period of the algebraic variety GM, is when you put the function 0. Right? So this is, of course, something that you see all the time when people use, for example, mirror symmetry of some toric varieties or stuff like this. So there's plenty of interesting things associated with this, like so with F, you have some polygon, and well, I know I'm not an expert in this. This function, it satisfies the differential equation. And the order is P plus Q. And you can wonder, now this function, it satisfies the differential equation of order P plus Q. We have one solution, one holomorphic solution right there. What are the other solutions? I can show you. So we are looking, where is the real part of F very large? So there will be, well, Q regions around 0, where because of this term, the real part of F, when your x approaches 0, becomes very large. And there is P regions, so here's like for P is equal to 2. There's P regions at the in the infinity direction, where again, the real part of F becomes very large. And what you can do is, instead of integrating around here, you can start an integration somewhere in a direction where F goes to infinity, and then end up into some other direction. So this gives you absolutely converging integrals. They define other period functions, but these ones will have proper monodromy factors, so you cannot specialize Z equal to 0. But obviously not, because the cycle is not compact, so you cannot integrate constant 1 on this infinite line. But nevertheless, the integrals are well defined, and they give you the other solutions. So choose a basis of homology, I say, like in this picture, and you will see you have a homology group of rank exactly P plus Q, and these different integrals over the other cycles give you a basis of solutions of the differential equation. Vary the differential form in a basis of an appropriate de Rham cohomology, and then you will find a matrix of solutions, like it's a fundamental matrix of a order 1 matrix differential equation. So here, yeah?
P regions equal to Q.
Regions close to 0, yes. They are not Stokes sectors. They are not Stokes sectors. So the Stokes sectors, they would correspond to the critical values of F. So there's a different, they are in a different plane. These are not Stokes sectors. These are just the directions into toward which the real part of F goes to infinity. So where e to the minus F decays rapidly. Yeah, so this is one interesting example that maybe talks to mirror symmetrists. Good, and so I've talked about the history in the past. This is more or less what's going on in the present. The reason why I'm here is a question for the future, which is, well, now we have this fantastic algebraic geometry source of E functions. Do we get all E functions like this? So given an arbitrary E function, can we cook up the algebraic geometry that explains it? So is there a corresponding variety X, Y, and F, and so on, so that the given E function appears, well, in a period function of this algebraic geometry setup? And so this is in my view, is like a correction a little bit of Siegel's question. So now we have this more ample source of E functions. Do we exhaust all the E functions? there's a conjecture of Dwork and Bombieri made in the 1980s that asks a similar question for the G functions. So you remember the G functions is like the same like E functions, but without the factorials. So Bombieri and Dwork, they conjecture that the G functions have a geometric origin in a very similar spirit. And what we can show together with Javier is that the two conjectures are actually equivalent. So if this old conjecture of Bombieri and Dwork holds true or is false, then the question about E functions coming from geometry is true or false. Good, so it seems like a difficult problem. What I would rather do, instead, because I have no idea how to attack it, is I want to test, in my future project, I want to test this question, whether E functions come from geometry on some examples. But, well, the only source of E functions that I have like are a priori already coming from geometry. So there's not really anything to test, except there's one candidate about which I'm excited at the moment, and that is quantum periods. So I will write you I have 30 seconds to write you one power series, and it is this. N goes from 0 to infinity. So here's the coefficient, z to the n, and the coefficient goes like this. L from 0 to n half floor down, 3n minus 4l factorial, and then below L factorial, n minus 2l factorial, n minus l factorial, the whole thing squared. So there's not my invention. I took this power series from a paper by Kaspersky, Alessio Corti, was it Garibaldi? I don't know. So it's the usual codes. Yeah. So I'm apologies. I should have written this down. So this is an example of a quantum period. So the paper is full of power series like this, and as an afternoon project, I dare you. So it satisfies a differential equation that is built in the theory of quantum periods. I dare you verify the denominator condition for this. So show this is an E function, and then, well, does it come from geometry? So can you write down an integral representation of this power series? That's what I'm asking. In fact, so an integral representation, well, some integral over a topological cycle on an algebraic variety. That's what I mean precisely. So open question, is there any, I know the answer for this one. So you can guess, are quantum periods, are they E functions? And if so, do they come from geometry? So in general, it's probably a difficult question, but so here, this is a quantum period for some Fano threefold. And I can give it to you. So it's I have taken it from, copied from myself several times. So maybe I should check. I don't remember which Fano it is, but so there's one of the examples. So do quantum periods have, well, are they in general E functions, not just in this example? So are they E functions in general? And if so, well, these do not come a priori from geometry. The question, do they come from geometry or not? That's something I would be very interested in knowing. Okay, so I'm 2 minutes over time. Apologies for that, and I finish here.
What is quantum?
You have to ask Giordano.
So it comes from quantum cohort. So what is the quantum powers here? What we are considering is the deformation of quantum powers. into which I mean the deformation is performed by introducing counting numbers of rational curves on the variety of the Fano variety, the Fano tree with other number. So this is to say that the word of quantum just appears because it comes from quantum cohomology. That function is in particular a solution. That section from the zero order universal system is just one flat section, the harmonic flat section of a broken connection that on the continuous manifold defined by the quantum cohomology. Quantum. So quantum periods are Gromov-Witten objects which encode information about the numerable geometry.
Yeah. So these, if you want, these coefficients that count. These coefficients that count rational curves on a Fano threefold with certain conditions. So that's, well, it's not an integer. So it's counting in a sense, but still, so there are intersection numbers on a moduli space of rational curves on a Fano Fano threefold, and well, you organize them in a power series, and that, I mean, from this point of view, it's very surprising already that there is a differential equation, right? That means, well, if this has some differential order, you can, well, count by hand the first couple of coefficients, and then the machine runs. So that's surprising. On the other hand, there's all this theory of the quantum cohomology behind, which tells you, well, explains why there are these differential equations. So what I understand is quantum is, in a sense, it's a deformation of the like a classical thing. Yeah. Yes, indeed. Yes, indeed.
Is the historic ever been employed also? Do you get a particular subclass of equations if you start? First question would be whether this Fano threefold is historic, and the second would be whether this class. I mean, the example is one dimensional historic, right? Just you have C star and you have the device.
So again, if I remember correctly, this one was kind of an exceptional example, so it's probably not toric. But again, apologies. I should check which Fano threefold it comes from. So I haven't this in memory. The other thing you say, like, sure, there's a subclass of like the E functions coming from Laurent polynomials but I gave you just for one variable. You can do this in several variables, of course, and that gives you in the space of all E functions a very small subset. So most E functions are not, well, they are not hypergeometric. They are not they're not coming from Laurent polynomials. I mean, if you compare, like, you have all the possible geometries for X at your disposal, and now you say, oh, I'm specializing to X a torus and the function f a Laurent polynomial. That's a very poor. It depends on your point of view, but from the point of view of the whole class of E functions, it's a very thin subset. But it's an interesting subset to work on examples. There is always this one holomorphic solution that is given by integration over a compact cycle, and that makes it on the other hand, interesting.
When you ask them, do you play around with divides of